Perfect. Well, good evening, everyone. The usual technical difficulties that you described this as. So what we're going to be doing today is essentially section 12.4, which is the cross product. So we've got two sections to cover this week, and this is one of them. I'm definitely going to get this section finished. I'm not sure how much, if any, of the next section we'll get. And if we don't, then we'll do the next section tomorrow. No, we went Wednesday. And I hope this is just a temporary glitch, otherwise I'll have to get a new set of mic combination earphones. So jump right into here. And this is essentially the main features in this thing called the cross product. So before we get started with calculating various things, I want you to imagine that we have two vectors in 3D space. So there's my vector u, there's my vector v. So imagine that's u, right? This is v. Right? Since they're in 3D, the chances are that they'll probably look like that, right? They're floating in space. There's a third vector called the cross product. And the cross product is typically written as u, a bit like a capital X, and you read that out loud as u cross v. And we call this the cross product of u and v, u cross v. And what it is, it's a vector that has a very interesting property. I'll try and draw it up here. Imagine this is the vector u cross v. And what's its special property is that this vector is perpendicular to both u and v at the same time. So can you imagine that there's another vector called u cross v that's perpendicular, orthogonal to u, and at the same time it's also orthogonal to v. So if I pretend that these are my two vectors, right? Then this green vector, if I orientate it one way, can you see it's definitely orthogonal to the blue pen? If I orientate it a different way, can you see it's orthogonal to the red pen, right? It's perpendicular or orthogonal to the two vectors u and v. And our job in this section is to calculate the cross product and to look into some of its uses and some of its properties. Now, there is actually a formula for calculating u cross v, like the dot product, u1, v1 plus u2, v2 plus u3, v3. Remember that formula? There is a formula for the cross product, but nobody uses it. What we're going to show you instead is how to calculate the cross product, but it's more of a process rather than a formula, right? So that's a little bit different. A process to calculate something, right? Like you do this, then you do this, then you do this, and you get the answer, rather than a formula where you just plug things in and hopefully you get your answer. Now, in order to find the cross product, we're going to have to do a little skill building exercise. We're going to have to find what's called the determinant of a 2 by 2 matrix. So if you've never seen a matrix before, there is a matrix. It's basically a table of numbers, right? A matrix is a table of numbers. This one is a 2 by 2 matrix. And that just means it's got 2 rows and 2 columns, right? It's got 4 numbers. So a 3 by 3 matrix would be 3 rows with 3 columns, right? And a 10 by 10 matrix would be ridiculous, but if you wanted one, it would have 10 rows and 10 columns. And we're going to find what's called the determinant of this matrix. And to do that, you multiply these two guys together, and they're called the major axis. And if you multiply these two together, that's 2 times 1, you get 2. And then you subtract. the minor axes. And the minor axis are these two guys. So to get the determinant of a 2 by 2 matrix, you multiply the major, take away the minor. So in this case, 2 take away 15. And the answer would be negative 13. Are you comfortable with that process, or do you want me to do a couple more of getting a determinant of a 2 by 2?
Can you do one more example?
Sure. So suppose it's negative 3, 3, 2, 7, right? Just some random digits. The determinant of this matrix is the major axis, which is the major diagonal, negative 3 times 7. Take away the minor. Take away 3 times 2. So this is negative 21. Take away 6. This answer would be negative 27. So major, take away minor. In fact, you'll see me doing this with my fingers a lot today. Major, take away minor, right? It's quite visual.
What determines the major and the minor axis?
The major always goes top left to bottom right.
Oh.
So the red one is always going to be the major, and the other one's going to be the minor.
Okay.
Okay, so that is how you calculate the determinant of a 2 by 2 matrix. And that's one of the things you'll need to know to come up with this guy that we've been talking about, this guy here, the cross product. Right. So let's move on to, is that enough, or do you want to see one more of these?
I think just the one is good for me.
Right, you were good then. Right, so next process. Suppose U is 7, 1, negative 2. I'm just picking two vectors at random, and we're trying to find the cross product of those two vectors, right? So we're going to find a vector that's perpendicular to this one, and it's perpendicular to that one, right? This guy called the cross product. And later on tonight, we'll find out why you would even want to find such a vector. It's quite interesting, the things that you get out of finding this guy. But right now, we're just going to find the cross product. So step one in this process is that you're going to create a 3D matrix. So it's a 3 by 3 3D matrix. And so the first row are the vectors I, J, and K. Can you remember those guys, I, J, and K? The basis vectors, one in the X, one in the Y, one in the J. This is one of the few times where I actually like the I, J, K notation because it's helpful. You know, most of the time I try and avoid it, but in this case, it's actually the only real way you can do it. The second row of the vector is always going to be whoever's first. So remember, we're doing U cross V here, right? So it's U, so that's 7, 1, and negative 2. And then the last row is V. So the way you create this 3 by 3 matrix, this three-dimensional matrix, is the top row are the vectors I, J, and K. The second row is the vector U, and the third is the vector V. Are we comfortable about that structure, how you create this guy? So far, so good? I, J, K, the three numbers that make up the vector U, the three numbers that make up the vector V. The step two is basically, get the answer. We're now going to calculate what U cross V is equal to. So this is a bit weird, but you just follow it. The answer is going to be some number of i's, right? So many i's. Then you're going to subtract so many j's, and then you're going to add so many k's. So there's going to be a number there. That's going to be like 3, that's going to be like 5, and that's going to be like 2 or -2. Notice the pattern's a bit weird. It's an I, take away the j, add a k. This is always going to be the case. It's going to be some number of i's, take away some number of j's, plus some number of k's, right? That structure is fixed. Doesn't change from question to question. Plus, take away, plus. Now, all we need to do now is figure out how to get these numbers. And I'm seeing if I've got a pen that'll work. This one will work. Let's get the number that goes in the I position, right? The guy that goes here. You cover up the column that's got I in it, right? So to get this number, cover up the guy that's got I. Technically, cover up that guy as well. Do you see a little baby 2 by 2 matrix? We will find that guy, right? We are going to find, right, the determinant of that 2 by 2 matrix. So let's see how it goes. 1 times 1 is 1. Take away 2 times -2 is -4. So major diagonal is 1. Take away -4. And that becomes 1 add 4, and that gets me 5i. So there's the first piece of my answer, right? It's going to be 5i. Now, if we move on, okay, I guess that's going to do. Found a solution to my problem. If the thing wouldn't stop rolling. There we go. You can see it's quite visual, this thing, right? It's a process. If you want to get the j term, do you notice that you destroy the column with j and you're left with, guess what? Another 2 by 2 matrix. Do you see it? And you find the discriminant. So 7 times 1, the major diagonal, is 7. Take away 3 times -2 is -6. And you're going to get negative 7 add 6 is 13. And you're going to get -13j. Right? Negative this answer, -13j. Now to do the last one, cover up the k. 7 times 2 is 14, the major. Take away 3. 14 take away 3 gets you 11. And so here is our answer as an I, J, K. I prefer, so that's a matter of taste, I prefer the answer to look like this. So the cross product, the vector that is orthogonal to U and V is this guy here. Well, I don't want you to just take my word for it. Let's check to see if it actually does do what it says it does. If this vector is orthogonal to that, doesn't that mean it's at right angles to it? Agreed? And it also is going to be at right angles to the other one. Now, 90 degrees, orthogonal, right angled, right? Orthogonal is the best of the 3 words. I'm going to check it and see if it works. So what would the dot product of this vector u with this guy be? Well, if it's orthogonal, shouldn't the dot product be 0? Right? So I'm about to, I hope, prove that I haven't screwed up. So it's going to be 7, 1, -2, dot product with this fella, 5, -13, 11. Right, dot product, 7 times 5, plus 1 times -13, plus -2 times 11. This guy is 35. This is take away 13. This is take away 22. Am I good or am I good? Would you agree that this cross product is at right angles orthogonal to you? Right? If its dot product is 0, that's the case. Now, let's try it with V. If this cross product indeed is what we said it is, shouldn't this also be equal to 0, right? Because these two should also be orthogonal. And the vector V is 3, 2, 1. And the dot product with the U cross V guy. So it's going to be 3 times 5 plus 2 times negative 13 plus 1 times 11. This guy is 15. That makes negative 26. This guy is 11. Bingo. Have I convinced you that U cross V is in fact orthogonal to the vector U, and it's also orthogonal to the vector V? That's pretty impressive that this weird IJK, major takeaway minor, all that whole process comes up with this special vector and it does exactly what it should do. Are we good so far? Right, let's do another one, right? There's a lot going on in that one. So, since I'm going to do another one, and I want to show you that it is totally, it works in virtually every situation. I'm going to pick you, Calvin. Give me 3 numbers for you. So it's totally random. I'm not making them up.
2, -7, and 14.
Okay, pretty big numbers. Natalia, you want to chuck in 3 guys for V?
Yeah, let's do 5, 2, and -6.
Right. So if we do the cross product of this, what we will get is a vector that's 90 degrees to this vector and 90 degrees to that vector. So we'll set up the 3 by 3, the 3-dimensional vector. It's going to be I, J, and K. Since U goes first, 2, -7, 14. V goes next, 5, 2, -6. Are you all comfortable with step 1 in this process? IJK, the numbers that make up U, and the numbers that make up V. Are we comfortable where they go and the order we write things? Right. Now, the next bit is where the rubber hits the road. It's going to be so many I's, take away so many J's, plus so many K's, right? First guy, take away second guy, add the third guy, right? That's always the case. And then we start doing, you know, rubbing out rows and rubbing out columns. So to get this fella, we cover up column I and the top row. And what we have here is a 2 by 2 matrix. Major diagonal. Well, if you multiply these together, you get 42. Take away minor diagonal. You multiply those guys, you get 28. 42, take away 28, leaves you with 14. So there it is, 14i. We got our first answer. Now, if you cover up the J guy, the column that's got J in it, you'll get the J number. Now, the major diagonal is 2 times -6, which is -12. Take away 14 times 5, which is 70. That gets me negative of -82, which I probably should have done in my head, but too late now. Ends up getting me positive 82. Are you comfortable about the negative of the negative gets you a plus? Now, the last one in the list is K. So you cover up column K, and you're now left with 2 by 2 matrix. The major diagonal is 4. Take away the minor diagonal, which is negative 35. So what you get here is 4 add 35, which is 39. And so the cross product of u and v is equal to the vector 14, 82, 39. How's it looking, guys? I'm not saying I've made a mistake, but if I have, this would be a good time to point it out. Now, I don't want to double check everything because that would just double our workload. So I'm going to only choose one of these two just to check this out. It's good to have a check, especially if it was a test question, right, where you don't know if your answer's right or wrong. So do you want me to check it with you to make sure that this is orthogonal, or do you want me to check it with V? Pick one for me and I'll do it. U or V, which would you like me to check it against?
Why not against you?
Why not indeed? So if this works, shouldn't the dot product be 0, right? Because that means when the dot product is 0, the two vectors are orthogonal. And the vector u is 2, negative 7, 14. Dot product with 14, 82, 39. Would you agree if this ends up being 2, it ends up being 0, isn't this too good to be just with coincidence, right? It must be that this method works, right? The numbers are too weird and random just to be a lucky, 2 in a row lucky dip. So 2 times 14, add negative 7 times 82, add 14 times 39. Of course, I left my calculator. Yep, I left it in my office at OC. I can tell you that one's 28, and 7 twos get me 14, carry 156. So that one gets me negative 574. That one's a bit too hard for me to do. Could somebody tell me what 14 times 39 is?
546.
Now, if you add that guy and take that guy away, perfect fit, right? 0.
Yep.
Can you move the paper up just a little bit? Even though it's 0.
Yeah. Are we good? So if I gave you any two vectors u and v, do you feel comfortable that you could calculate the cross product u cross v? Right. And if you wanted to, do you also feel comfortable that you could do the dot product check just to make sure that your working is okay? Okay, then I'm going to give you one. I'm going to give you, I don't know, 3 minutes to see if you can do it. You only need to get to there, right? If you've got time, then do a check, but you don't need to if you don't have time. I'm not going to go huge, but I am going to go weird. Okay, find the cross product of those two guys. You've got 3 minutes to do it. No pressure. Okay. Last few seconds coming up. Let's go for it. Calvin, you feel up to doing the I one?
Sure.
So I'm covering it up for me. You tell me what you write down.
-3 and 0. So just -3 actually. -3i.
You got it. Natalia, you want to go for the J?
Yeah. It was -1 minus 0, which is just when you do it, it would just be 1j.
Yeah, because two negatives work
Yeah.
together. Correct. Okay, I'll do the K. There we go. Cover that guy up, cover that guy up. 5, take away -6, which actually becomes 11k. And so our cross product is -3, 1, 11. We all comfortable? Hopefully you all got the same kind of numbers.
Yep.
Okay, so we can check that off our list. And I think we can check that off our list. Have we done enough of them? You feel comfortable that if you got two vectors, you could do the cross product, right? So I know I'm still on that, although I said we could cross it up. But there is a homework question that does something that looks like this. The two vectors u and v that we're going to find the cross product of aren't numbers. Do you see that almost all of them have t or t squared or something in it? And we are still going to get the cross product. The difference is that our answer will not be numbers, right? It wouldn't surprise you. Won't these be things with t's and t squares in them? But the process stays the same. So we have an I, we have a j, we have a k. And this guy is 2t, this is 3, and this is t squared. And this is t, and this is t squared. And finally, this is t cubed. Would that be, I hope, the way you would have tackled this question if, you know, it just appeared out of nowhere? So what we can now do is so many i's, take away so many j's, plus so many k's. Right? And that's what we would have done if these had all been numbers. So if you cover up the i's, you've got major diagonal 3t cubed, take away the minor t to the 4. So 3t cubed, take away t to the 4. If we then move to do the j term, major diagonal 2t to the 4, take away a t cubed. 2t to the 4, take away a t cubed. And last but not least, the k's. Major diagonal 2t cubed, minor diagonal, take away 3t. And that would become 3t cubed, take away t to the 4, subtract that guy, and you could rewrite it in two different ways. I'm just switching places. And then this guy. This one here, you could have written it as -2t to the 4 plus t cubed, but I think that looks prettier, so that's the only reason I did it. Any problems with that? Or, yeah, it's really the same process. It's just I don't have numbers so much. I've got x's and t's or t cubes, whatever it might be. Okay, I'm about to look at this fella now, the third thing. I want you to imagine that I did a cross product of u and v, and the answer ended up being the zero vector, which can happen, right? It is possible for this to happen. Something is interesting is going on with the vectors u and v. The only time this will happen, unless one of them is just a zero vector, and that's silly, right? The only way that's going to happen is if u and v are parallel. So if you imagine that was u and this is v, can you see that there isn't a single vector that's orthogonal to them? You might say, well, I go, that one's orthogonal, which is right. But isn't all the other ones that make a wheel shape also orthogonal to that? Can you see that? There's an infinite number. So how does that work out as cross products? If the cross product is a zero vector, u and v are parallel. So there's a test for two vectors being parallel, right? Cross products are zero. Right? Parallel. Now, if I find the cross product of u and v, let's say it's 1, 2, 3. What do you think you would get if you switched the u and v around? So instead of the u going on the second row and the v on the bottom, the v went in the second row and the u went in the bottom. What do you think the answer would look like? It's not the same answer, but it's similar. Any guesses? So what does that tell us? The property could be written like this. The cross product v cross u is the negative of u cross v. So you see that they're not equal to each other, but they are negatives of each other, right? And can you remember the right hand and the left hand rule things that are going on? Cross products are right hand rules. If you switch places, the thumb points downwards, right? If you do u and v, v and u, do you see your thumbs pointing down the way instead of up the way, right? So I guess that's something to do with the right and left hand rule, who for some reason, some engineers find that helpful. Cross products, good. So we know how to calculate them, and we know a few properties. Let's move on to the main meal of today, and which is using cross products to find all sorts of things. Now, imagine this is vector u, and this guy here is vector v. And let's just pretend that we did the cross product and it was 1, 3, -2, right? Now, if you find the magnitude of the cross product, and this seems totally weird, but if you find the magnitude of that vector, it's going to be 1 squared plus 3 squared plus -2 squared is going to be the square root of 14, right? So that is a number, right? A scalar. That square root of 14, the magnitude of the cross product, has a meaning. It actually represents something. If you take this vector here and you draw another guy parallel to v and another guy parallel to u, do you see you make a parallelogram? Right? Can you imagine adding another U, adding another V, right? You could make it's not the best drawing parallelogram, but it's a parallelogram nonetheless. The area of the parallelogram is that. Now, come on, that is weird. That the magnitude of the cross product is the area of the parallelogram made by U and V. I mean, if you were going to guess, I doubt that's what you would have guessed what the square root of 14 represents. Agreed? That doesn't even seem intuitively correct, but nonetheless it is. Now, remember that guy that we did where the cross product was 0, 0, 0, right? Remember that guy? If you find the magnitude of the 0 vector, isn't the answer 0? If you had two vectors that are parallel, would you agree the parallelogram wouldn't exist? It would have an area of 0. Do you see there's a small overlap between this property and that one? So, parallelogram. Suppose you wanted to know the area of this triangle. Right? The one formed by U and V. If you want to know the area of that triangle, it's half the square root of 14. It's 1/2 the magnitude of the cross product. And the area is the magnitude of the cross product. That one's not so difficult to understand. Would you agree that a parallelogram, if you split it, makes two triangles of equal area? So wouldn't the area of one of the triangles be half the area of the whole parallelogram? Any questions about that? You can use the magnitude of the cross product to find the area of parallelograms, and half of that answer to find the area of triangles. It's quite interesting. Are we good so far? Any questions?
So what about the parallel of 180 degrees instead of 0? I know that's just a question I just thought of only because when we were talking
Right, so
about
if you're talking 180 degrees, are you meaning U and V are like these two bends?
yes, like that was the
Right.
two conditions, right? That were parallel, 0 and 180.
Right, they're also parallel, right? And the cross product of these would be 0. And the argument is that that red pen, get my fingers out of the way, get my fingers out of the way down here, can't win. Isn't that guy perpendicular to both vectors? But wait a minute, isn't that guy perpendicular to both vectors? Isn't any guy I want to rotate from here to here also parallel to that? Do you see there's no unique answer? And so what you're saying here is that if you have parallel going the same way, that's a 0 degree thing, or parallel going against each other, which is a straight line kind of situation like we have here. The cross product in both those situations is 0, 0, 0, because they're just two different ways of looking at parallelers, right? Two vectors can be parallel two different ways.
Okay, thank you.
Right. Now, to a question, P is the point 317, Q is the point 1, -1, 2, and R is the point 530. So here are 3 points in 3D space. Let's pretend that's P, that's Q, and the way down here is R, right? And I asked you to tell me the area of this triangle. So my question is, what is the area of the triangle PQR? And all I'm going to tell you are the coordinates in 3D space of P, Q, and R. And we are going to use cross products to get that answer. And I know that looks like a right angle, but can you pretend it's 82 degrees or something? Because it doesn't need to be. Any suggestions? I don't need the details yet, but how you would approach getting the area of this triangle using cross products?
My intuition is to find two vectors connected to the same point
Mhm.
and then take the cross product of those.
Sounds like a good plan. I'm picking P because I like P, but you could pick Q, you could pick R. Good news is that you're going to get the same answer eventually, right? So the vector PQ would be 1 take away 3, -1 take away 1, 2 take away 5, 2 take away 7, -5. And the other one is going to be PR. And second take away the first, second take away the first, second take away the first. And we got those two guys. Okay. Now, I'm going to find their cross product. So I'm going to go I, J, and K. And this one's going to go first. So -2, -2, -5. This one's going to go second, 2, 2, -7. And in a few moments from now, we're going to get the cross product. But wait a minute, got to be careful here. I want the triangle. Once I've got that cross product, won't the magnitude give me the area of the parallelogram, right? So remember to half your answer when you're finished. Does that make sense? Half the magnitude of this vector. So many i's, take away so many j's, plus so many k's. You cover these guys up, you have 14 take away -10. If you do the middle one, you have -14 take away -10. If you do the end one, it's -4 take away -4. That's 14 add 10, so you get 24. That's -14 add 10, so it's -4, but take away another negative gives you a +4. And this is -4, take away -4, -4 add 4 gets you 0. So here is our cross product of those two fellas. Now to find the area of that triangle, I'm going to find the magnitude of this vector and then half it, okay? Area of triangle is half that. So here we go. The area of the triangle is 1/2 the magnitude of the cross product vector. Try and do this in my head. 1/2, oh, God in Himmel. 24 squared is 12 squared, which is 144 times 4. 144 times 4 is 526, I hope. Plus 16, plus 0. So 530, 542. So it's 1/2 the square root of 542. By the way, is 24 squared 526?
It's 576.
Wasn't even close. 580, 592 then. That's why you need calculators, at least I do. If the question was find the parallelogram, wouldn't the answer just be the square root of 592? If it's a triangle, which it is, it's half that answer. We good? So we're finding applications. Reasons for why we would want to get a cross product. This one is so that you can find areas of triangles or parallelograms. Let me nip over and show you what the homework questions look like. Now, the vectors can be called A, B, U, V, anything you like, so don't be put off by the fact these ones are called A and B. I like U and V myself. Here's a vector, here's your other vector, cross product goes in there. Now, if you want to do the cross product, make sure you hit the vector tab. I like that notation. I'm making this totally up, but can we pretend the answer is 5, 6, 7? If that's what the answer is, wouldn't you type that in? Right. Of course, you'll have to find out what it's really equal to. But what's the answer to B cross A? Assuming I got the first answer correct. So if A cross B is this guy, I really don't need to do a lot of work to find B cross A, do I? So what is the answer?
Negative of those values.
Yes. Now, in question 3, it's asking us to find, what's it doing there? It's a 2D one. That question shouldn't be there. I probably thought it was a 3D question when I made it. So that will disappear before the end of tonight. Right, back to this one. 2 vectors, find their cross product, put the answer in there. What should these 2 things equal? And it'll be a number if this worked. Well, wouldn't they both be zeros? And we've done two or three of those, right? Cross product dot A. I think I wrote it down like A dot cross product, but isn't that totally okay? Because cross dot products don't care the order. Only cross products care about the order. Right, and we done one like that with all the T's in it. Isn't this basically the vector 5, comma, no, it isn't. It's 0, 5, -8, and this vector is -1, 2, 1. When I do cross products, I don't like that notation. I like to turn them into the normal vectors because I think it's a bit easier. But that's the only difference. This one is pretty straightforward. And that's the way I like vectors to be written. So that one's a little bit easier in my brain. But aren't you just going to get the cross product and then just reverse them? This one, just ugly fractions, but nothing else. I get a feeling that one has just been done. No, it's similar, but not exactly the same. Pretty standard one. Now this one is a bit, oh, what am I saying? Right, it looks like it's a bit different, but it truly isn't. It says find 2 unit vectors orthogonal to that guy, right? So let me show you how you would tackle how to find 2 unit vectors orthogonal to whatever you're given. Normally when you get a cross product, right, don't you get vectors that are not unit vectors? Right, if you wanted to get a unit vector, wouldn't you just find the magnitude and divide everybody by it, and now you've got a unit vector? So along that same lines, I'm going to call the first vector U, and it was 6, 7, 1, and the second vector V is -1, 1, 0. And I'm going to find their cross product in the usual way. So I have an I, a j, and a k. And I have 6, 7, 1, and I have -1, 1, and 0. And it's going to be so many i's, take away so many j's, plus so many k's. So if you cover those guys up, you get 0, take away 1. If you do the middle, oops, you get 0, take away -1. And if you do, there we go. If you do the last one, you get 6, take away -7. And so we have -1. That guy's 1, but then you take its negative, and that's 13. And there is our cross product. And at that point, you then might hesitate and say, but I need to find two vectors that are unit vectors that are orthogonal to these. Right now, I've got a vector that is orthogonal to them, right? There's only one of them, but it isn't a unit vector. So that's what I'm going to do right now. I'm going to find its magnitude, which is the square root of 1 squared, technically -1 squared, -1 squared, plus 13 squared, which gives me the square root of 171. So here's my first vector. Actually, my first unit vector. It is going to be -1 over the square root of 171, -1 over the square root of 171, 13 over the square root of 171. That vector that I've just done is orthogonal to these. And the reason why it's orthogonal is, isn't it in the same direction as this guy? It's just smaller. Right. So if all you're doing is shrinking the size of something, but not the direction it's pointing, isn't it still going to be orthogonal to the first two? But that's only the first answer. They said, find 2. What could you do to this vector to generate a second one? And it's still got to be a unit vector, so you can't do much to it.
Multiply it by -1. Find the one going in the opposite direction.
Yeah. This guy is U cross V. Isn't this the one you would get if you did V cross U? And both of them are unit vectors now, so we've solved the puzzle. In their question, they want the smaller I value, so this one goes first, and then they want the larger I value, so this one goes second. This is -1 over, this is plus, so that's obviously small, that's bigger. How's that one looking? You comfortable? Snip over to the homework situation and see what else we haven't covered. Right. Ready to show you. We are being asked to find a couple of questions. That's one of them. That's basically question 13. And then, is there anything else? No, that's the only one. I thought there was 2, but that's fine. Now, it's a cross product of these two, and then whatever the answer is, you do a cross product with that guy. So I'm going to give you some properties involving the basis vectors, right? The I, j, and the k. So here goes. If you do I cross I, you will get the zero vector. Because isn't I parallel to I, and cross products of things that are parallel get you zero. J cross J is also the zero vector, and K cross K is also the zero vector. Does that seem reasonable? Now, if you take the vector I and you cross it with the vector J, you will get the vector K. So let's try and prove this one. Isn't that essentially the x-axis? Isn't that essentially the y-axis? So shouldn't the guy that's orthogonal to them, right? Shouldn't it be the z-axis? Does that make sense? I cross J equals K, and we're doing it with the right-hand rule. That's why it's positive K. What would J cross I get you? Oops, no, that's good. Well, yeah, I got it right way around. Keep changing my mind here. If I cross J is K, what is J cross I? Notice the order. If that's K, what's this guy?
Negative K.
Negative K. No. J cross K, it's going to trust me on this one, is I. So K cross J is negative I. Which one have I not done, J, K? And then K cross I is J. And then I cross K is negative J. And that's pretty much every combination of cross products of I, J, and K you could like. 3 of them lead to zero vectors. These 2 give you versions of K. These 2 give you versions of I. And finally, these 2 guys give you versions of J. Right, back to this question here. I cross J is K. So this becomes K cross K. And K cross K is the zero vector. And there's your answer. That guy up there is equal to the zero vector. Are you okay with that? So how about this? I plus, do it again. I plus J cross K. Now, I want to find the answer of that without drawing one of these tables. So essentially, I'm using the distributive rule. And doing that guy with I and that guy with J. I cross K is negative J. And J cross K is I. Technically then, couldn't I do any combination of I's and J's that I like and cross product them with any other I, J, and K? And as long as I use these rules here, shouldn't I be able to find out what all the answers of any combination of I, J, and K you could think of? In fact, if you do that, that's where this comes from. So if you wanted to go right into the nitty gritty, why is that guy a negative J when all the others are pluses? It comes because one of these ends up being this guy here. Right, in fact, this guy here. Unfortunately, there's only one example of that particular question. Quite a few one examples as well. Going to try and close something here if I can. And here we go. The next guy in my list of things, because we've done these two, is the volume of a thing called a parallelepiped. Shouldn't that be the name of an elf? Parallelepiped, a baby elf, right? Not a grown-up elf. I want you to imagine that you've got three vectors. You've got vector u, you've got a vector v, and then you've got a vector w. So emanating from a single point in 3D space, you have three vectors, u, v, and w. You can have them anywhere you like, it doesn't matter. If you draw a guy parallel to w and another guy parallel to v, do you see that those two make a parallelogram on the floor? If you then do a vector parallel to u and the same length as you, like this, and then you join that guy to that guy to this guy, to this guy, and finally to this guy. Oops, there we go. Okay, I'm not the best artist in the world. Can you see what is equivalent to a three-dimensional parallelogram? It's a bit like a box that somebody sat on and made it bend over. Can you see the shape that you've got there, right? Does that make sense? That shape is called a parallelepiped. A parallelepiped. It's a kind of tongue twister. We would like to know the volume of that shape. Now it's a three-dimensional shape, and its volume is given as u dot v cross w. You'll very often hear this combination of a dot product with two vectors being in a cross product. This is very often called a triple product. Now let's see what you generate when you do this. Would you agree that v cross w ends up being a vector? Right, it's a vector perpendicular to v and w. But isn't u dot another vector going to get me a scalar, in other words, a number, right? So the volume is the dot product of the vector u with the cross product of v and w. And then you have to do something. This volume, when you calculate it, will give you, this calculation will give you the volume. But sometimes the answer's 40, which is great because that shape is 40 cubic meters. But sometimes it's negative 40. And because sometimes the way the numbers come out is negative, we stick an absolute value around the thing, right? Now that does not that doesn't mean the magnitude of the vector. This is the good old-fashioned absolute value of something, right? So it's the same symbol being used in the way it used to be used, right? Just to mean absolute value. And the reason we need it is because this inside calculation is sometimes a negative number. And would you agree you don't want to say the volume of something is negative 30 cubic meters, right? That really is a bit of a weird answer. You want the answer to always be a positive number, and that's what takes care of that. So let's find the volume of a parallelepiped. U is a vector 1, 2, 4. V is the vector -1, 0, 3. And W is the vector 2, 1, 1. Now, since this is quite a complicated calculation, we're going to break it down into manageable stages. I'm going to find the cross product of V and W first. So it's going to be an I, it's going to be a J, it's going to be a K. And V is -1, 0, 3, and W is 2, 1, 1. And so many I's, take away so many J's, plus so many K's. Zero take away 3. -3. Middle one. -1 take away 6. That gets me -7, but a negative of a negative gives me +7. And lastly, -1 take away 0. That gets me -1. And here is V cross W, that guy. Next thing we do is we do the dot product. And so the vector U is 1, 2, 4. Dot product with -3, 7, -1. And this becomes 1 times -3 plus 2 times 7 plus 4 times -1, which is -3 add 14 take away 4, and the answer is 7. So in this case, I don't worry about the absolute value. Would you agree the answer is just 7? So there is your volume. 7 cubic meters. That thing is 7 cubic meters. Are you comfortable with the formula for calculating the volume of these weird shapes? Now, if I had done this calculation, but the answer had been -30, just for example, right? Can you imagine doing this and the dot product was -30? Wouldn't I then say, oh, call it 30? That's when the absolute value part would become relevant, right? So if the answer is positive, you don't even worry about it. It's only if the volume calculation comes out as a negative number, which by the way it can. It's just as likely to be a negative as a positive. Here is some interesting property about what we just did. I did U dot V cross W, right? If I had done V dot U cross W or W dot U cross V, although each one of them would generate different vectors, do you know the final answer in each case would be the same? So that's good news. Doesn't it mean it doesn't really matter who you do the dot product with? It doesn't really matter which two vectors you do the cross product with. As long as one of them's a dot and the other two get crossed, you are good. It's kind of interesting because it's not obvious that that should happen, right? You could imagine that if you switch the order, things would change, but they don't. Not the final destination, at least. The in-between numbers might be different, but when you get to the final answer, it's still 30.
So why is it 30? Did I miss something on the left page?
Oh no, I'm just pretending that this one was 30, right?
Okay.
Now this one is 7, so we're stuck with it. But I'm just saying, you know, actually, if I did any combination of these guys, Wouldn't the answer be 7 all the time? Right? That's all I was getting at. Now, 3 different vectors again. U, V, and W. And we do the triple product. So we're not necessarily calculating, although we might be a parallelepiped. Sometimes the answer is positive, right? Sometimes the answer is negative, so you stick an absolute value. But now and again, the answer ends up being the number 0. Now, on Earth, geometrically, does that tell me about the 3 vectors U, V, and W? You remember when 2 vectors gave you a 0, didn't that mean that they were in fact parallel to each other, right? But what does it mean if the triple product is 0? Any ideas before I tell you? Geometrically, what do you think it might mean? Okay, here goes. I want you to think of this as a plane, right? A plane would be, you know, an angled flat piece of paper, right? If the triple product, that's another name for this calculation, if it's 0, the number 0, then the vector U, the vector V, and the vector W are all coplanar. That means that they all lie on the same plane. You notice that they're not parallel to each other, but they're all, imagine this was a plane, right? See, they're all on the same piece of paper. None of them are sticking outwards, right? Now, if you try to create a 3D shape with that, wouldn't you get a volume of 0? Because there's no height to it. So that's a property that allows us to tell if 3 vectors are coplanar, meaning they all lie on the same plane. So if the triple product is 0, they are coplanar. So let's put 2 properties together. If the cross product is 0, then we can say that U and V are parallel. Agreed? If the triple product is 0, then the 3 vectors are coplanar. So this cross product thing keeps popping up in all sorts of unexpected ways. It allows us to get areas of parallelograms, areas of triangles. It allows us to find volumes of parallelepipeds. It also allows us to tell if 3 vectors are parallel, or sorry, 2 vectors are parallel, or 3 vectors are coplanar. Do we have any questions?
So does that mean one of their X values are all the same or their Y values are all the same? Like if you had a,
Not necessarily. That would be true if the plane was, say, like parallel to the XY or parallel to XZ. But the plane could be an angle. And coplanar just means that you can draw all 3 on one piece of paper, one plane. So
okay.
it wouldn't necessarily mean, although that would be an example of it happening, there are other examples of being coplanar where that's not true, right? They're coplanar, but their x's are different. and their y's are different, and their z's can be different, because you can, if you're on a diagonal plane, you've got a lot of variation about where you could be. The only thing that's fixed is that you're all on the same piece of paper. That's kind of the coplanar thing.
Okay.
Now,
I'm not exactly sure how you would identify something like that.
how you would identify coplanar?
Yeah.
Oh, all you do is find the triple product, and if it's a zero, they're coplanar.
Okay.
So if I said to you, here are three vectors, are they coplanar, yes or no? You would calculate the triple product, and if the
Oh,
answer
okay, so
was
you still have to
42, you would say
calculate.
no, right? You have to calculate it, right? You would, if you got the answer 42, you would say they are not coplanar, and if you got the answer 0, you would say they are. Now I'm making one big assumption here, but it's a pretty sensible one. Would you agree that you don't want any of the vectors to be the zero vector? Because if any of the vectors are zero vectors, isn't the answer kind of stupid, because everything ends up being zero, right? If U was a 0, 0, 0 vector, wouldn't its cross product, its dot product, any other kind of product, wouldn't it just be zero, because the zero vector basically destroys all calculations, right? So we're making the assumption all the way through everything we've done today that none of the vectors are zero vectors. I think if any of them were, you would notice. So it's not a difficult assumption to make.
Thank you.
Are we good? Right, that was a good question. Any other questions? Then let's continue with cross products and another situation. Here are three random vectors, u, v, and w. You can find, or it's possible to find, this calculation. So it's u cross v cross w. And this can equal things. It doesn't have a very good geometric interpretation, right? It is a vector when you're finished, right? So it doesn't represent a volume or an area or anything, right? Okay, and it's, I'm trying to panic here or think a reason why I would want to find such a thing, but for the life of me, I can't think of a good reason, except that you do get asked to do them. So let's figure out how you do it. If you were going to calculate this, you kind of need a game plan, right? I'm going to do this first, and then I'm going to do that. Based on what you're looking at here, what do you think would be the game plan? What do you think you would do first? And by the way, question 15 is like this one. What would you do first?
V cross W.
Agreed. Wouldn't you need to know this guy before you could do that, right? Right, so jump right in. Let's find those two guys. Okay, we should be professionals at doing these things by now. So many I's, take away so many J's, plus so many K's. So 10 take away 8 gets me 2. 0 take away 4 gets me -4. 0 take away 2 gets me -2. And so the answer is 2, +4, -2. Now you want to do u, which is this vector. cross this guy. So a little bit on the quick side. You would put that in. You'd have an I, you have a J, and a K. The vector U is 1, 2, -1. The cross product is 2, 4, -2. And so it's going to be so many I's, take away so many J's, for so many K's. -4, take away -4, just it. -2, take away -2, just it. 4, take away 4. There is no reason in the world why I got the 0 vector. It could have been the vector 1, 2, 3, could have been the vector 0, 0, and 52, right? Could be anything. By sheer good luck, or more likely bad luck, haven't I just randomly picked some vectors that ended up being 0, 0, 0? Can you trust me that when you do that in general, you just get some three-dimensional vector, right? It's not 0, 0, 0 every time, in case you're thinking that, right? It just happens to be that this one weird connection. What I strongly suspect is that the 3 vectors that I randomly chose at the beginning, these 3 vectors up here, I suspect that they're connected in some way. And that's why this 0, 0, 0 is happened. I can tell by the fact that this guy crossing that guy is 0, that these 2 vectors, right, because their cross product is 0, does it not make these 2 vectors parallel to each other? So evidently the vector U is parallel to the orthogonal vector to these 2. That was just a fluke of numbers. But the process is correct, right? That's how you find U cross V cross W. Now, here is something I want to make sure I'm telling you the truth about that type of calculation. I'm trying to get the answer here to double check it. Can we pretend a different question? Because you won't be able to see what I'm about to do if we have a 0 vector. Can we imagine I picked some other vectors and that was my answer, right? Just totally different vectors, and I got this. Suppose you decided to change the order. Suppose, for instance, you decided to do U and V first, and then whatever that answer is, cross product it with W. So it's still the vectors U, V, and W, but you see the order I'm doing is these 2 first and then U. And now I'm going to do these 2 first and then W. Do you think these 2 answers should be equal to each other? Do you think this answer should be the same vector as the original? Does that seem reasonable? It does sound reasonable. But the answer is that they're not equal. They're not even the negatives of each other. If you did this vector with a random combination of vectors, right? Pick any U, V, and W you like. do this calculation, then do that one. These two answers won't have anything typically in common unless you got really unlucky and got a zero vector. And that's pretty much the end of
So
this
you're
section.
saying it's the same value, it's not negative this time?
No, it's not even the same value. It's not equal to it. So
Oh, it's not equal. Okay.
yeah, that's a not equal to it. You might get the answer 7 to 43, right? It'll just be three numbers with nothing particular in common with the other one. So no connection, essentially, or no obvious one at least. Okay, right. So let's show you the last couple of questions and then we can get a little head start on the next section. We only have two this week, so kind of good that we only have two. Not sure where I am, so let me try that again. Are you looking at 24? Is that what you're saying? Question 24 example.
Yep,
Video.
we're seeing question 24.
Right. So watch a video and it takes you through how to find the cross product. You see it's kind of messy, but it is there, right? If you do question 25, watch the video and it takes you through this guy. And there's your two cross products. And I thought, and I may be wrong, that they have a question that has the formula in it. And I don't think they did. Oh, I did miss somebody. I'm glad I did the last check. Suppose you're being asked to find the magnitude of that cross product, right? But all you are told is that the magnitude of this vector is 6, and the magnitude of vector u is 10, and that the angle between the two of them is 30 degrees. Can you find the magnitude of the cross product? And the answer is you can. And the answer is it's the magnitude of u times the magnitude of v, followed by the sine of the angle in between. So in this case here, the magnitude of the cross product will be 6, no, let's get it in order, 10, that guy, times 6 times the sine of 30 degrees. And there you go. So that was a little baby question, I missed that. Are we good? Last chance, if you've got any questions about cross products, this is your opportunity to ask me. Otherwise, we'll be moving on, as I said, to our, at least the start of our next section. Okay, I'm going to put a stop on that and close this off and start our last section for this week. And we're going to be looking at section 12.5, and we're going to be looking at the equation of a line in three-dimensional space. Actually, we aren't going to do it today, but we will do it on Wednesday. We are also going to be looking at the equation of a plane in 3D space and the interaction of lines and planes in 3D space. So far, so good. Imagine this pen is a line in 3D space. And I would like to find an equation that would allow me to find the coordinates of any point on that line, right? That line goes on forever. Well, normally to do that, don't you find an equation for the line? You know, like in 2D, wouldn't it be y equals 2x? And if you knew the equation of the line was y equals 2x, so let's imagine that. Couldn't I find the coordinates of any point on the line? So for instance, if I knew the x coordinate is 3, wouldn't the y coordinate just be simply 2 times 3 is 6? And therefore I could tell you that that point there had coordinates 3, 6. Great. That's equation of a line in 2-dimensional space. That isn't even vaguely like what the equation of a line looks like in 3D space. If you do, and I'm going to set it up right now, if you go into GeoBra and you type that guy, you will not get a line. Let's find that guy and show you what you do get. Come on, GeoBra. There we go. Okay, it's loaded up. Right, so if you go here and you say y equals, what's it going to be? 2x, yeah. And you go y equals 2x. Do you see that the answer you get is all the points on this plane? You see, it's a diagonal plane. You see it? It's not a line. So 2D into 3D isn't simple, right? The equation of a line has to take on a new meaning and a new way of doing it. So we are now going to look at how we, in fact, do the equation of a line in 3D. First thing you need is a point on the line. And it can be any point, so it's in 3D space. So my finger is the point, and let's pretend that point happens to have coordinates 1, 2, 4, right? That's the first thing you need. The second thing you need is called a direction vector. So, and rather than me trying to point in 2D space and you're not really seeing what the heck I'm trying to draw, I want you to imagine that that guy there is floating in 3D space. That's where P is, right? Now, if you have a direction vector, it's a vector, normally it's called V, and it tells you that's the direction of the entire line. Now, if you continue that line forever, both forward and backwards, do you see that you've now created a line in 3D? So let's suppose that this direction vector was 5, -1, -2, just for argument's sake. Then how do we express the equation of this line? Well, there are 2 ways in which you can express it. One is using what are called space curves. 2 is called, what's the name of them? I'm trying to remember what the name of these are. I think it's called standard form. I may change that name overnight. Look it up. It's called standard form. And now I've actually got a third version. It's called the vector equation. So there are 3 ways in which we can describe all the points that lie on this line. Let's look at the first one, space curve. To do a space curve, a space curve has this general format: f of t, g of t, h of t. So it's basically a parametric equation in 3D. So this wouldn't be a straight line, but it would be a space curve. If I said to you t squared 2t minus 1 t cubed, right? That would be an example of a space curve. what that would do is it would tell you every single point on that curve. All you do is plug in a value of t, and won't you get a position vector for it? A position vector is the vector from the origin to the point. So in fact, a position vector is the same as telling you the coordinates. So if I had a position vector 1, 2, 3, that would mean from the origin to that point was 1, 2, 3. Isn't that just another way of doing the coordinates? So it's a kind of vectors, but the vectors themselves are called position vectors. They allow you to get the equation of the curve. So for this fella, this is, oh, let's generalize it. P is going to be the point x0, y0, z0. V is going to be the direction vector A, B, C. And the equation of the line, the space curve as we would generally call it, is the following. It's going to be AT plus x naught, BT plus y naught, and CT plus z naught. So if I gave you the point 1, 2, 4, that's x naught, that's y naught, and that's z naught, and this guy is going to be A, B, and C, then the space curve for this straight line would be 5 times t plus 1. Then it would be negative 1t plus 2, and then it'd be negative 2t plus 4. So do you see how you create the equation of a line in 3D by using a parametric equation called the space curve? It's A, B, C, the direction vector, attached to the t's, and the 1, 2, 4 is essentially that point. Give you an example. If I evaluated this space curve at t equals 0, wouldn't I get 1, 2, 4? Wouldn't that be the coordinates of the point 1, 2, 4? A position vector is equivalent to a coordinate, right? A position vector is a vector from the origin to that guy. Well, isn't the origin to that guy the same information as the point 1, 2, 4? Seeing if I can put this guy in for a second. Bear with me. Okay, let me show you what I've just been typing. I probably should have showed you as I was typing it. Too late now. Hey, it was there. Where'd you go? Oh, it's turned it into a vector. That's not nice. I don't want that. Can I do it another way? Let's try this guy. I'm just trying to make GeoBra plot the thing without going into weird things I don't want it to go into. Yeah. Now, before I touched it, can you see that black line? See it there? This guy
Yep.
here? Now, there. Can you see that is a line in 3D? And the equation for it, I know GeoBra has got a nasty habit of taking what I just did and turning into the vector version of that equation. Right? It's the same equation, it's just written a different way. And can you see what it used to look like before I let GeoBA get its ugly paws on it. The version that I wrote down with the brackets is this guy here. So there is the equation of a line in 3D. So let me try that again and show you. I now remember what this thing is called. It's called the symmetric form. Right. The first version that we just did, even although GeoBra changed it almost immediately after I wrote it, was the space curve version. The second way of writing that down is its vector format, which is what GeoBra did. And it wrote it like this guy. 1, 2, 4 plus t times 5, -1, -2. Do you see that is the coordinates of P written down as a position vector? And isn't that the direction vector V? So as long as you know these two things, can't you create the equation? You can write it down in this format, which is the vector format. You can write it down in this format. Basically, if you do that, doesn't it turn into this? If you do a little calculation, t times that, then add it to 1, off you go. Now, the third one is the weirder one, and that is the symmetric version. Of a straight line in 3D. So let's imagine we've got our point P, 1, 2, 4. That's basically the x naught, the y naught, and the z naught, if you want to generalize it. And you've got V, which is your direction vector. And that's essentially, in this case, it's 5, -1, -2. But in general, you could just call it A, B, and C. The symmetric version of a straight line looks like this. X take away x naught over A equals y take away y naught over B equals z take away z naught over C. Now, if you put in the numbers, right, the x naught, the y naught, and the z naught, and the ABC, right, what you have is x take away 1 over 5 is equal to y plus y, got it wrong here, y minus 2 over -1 equals z minus 4 over -2. And that package is called the symmetric form of the equation of a straight line. These two are almost identical, aren't they? They're just slightly different ways of writing the same thing. Would you agree this one is quite different in looks to these two? Now notice what happens. It's minus, minus, minus. -1, -2, -4. And on the bottom is the direction. 5, -1, -2. You see the position of each of these pieces? Now, if you wanted to take this equation and rewrite it so it looked, say, like this one, it is possible to do it. I mean, it's pretty easy to change these two into each other, right? It's less obvious how you're going to change this guy into, say, the top one. So let me show you what you do. You take this guy and you make him equal to t. If you do a little cross multiply, you get that. And then you add 1. And now you have the x guy. You see where it came from? Make this fraction equal t, solve for x, you get this guy. If you take the second one, which is y take away 2 over -1, make him equal to t, a little cross multiply, and then add the 2. which gets you that guy. And then for completeness sake, you do this one, which is z take away 4 is minus 2. Make that equal to t. Do a little cross multiply. And then add 4. And there's your third guy. So this version, which is the space curve, this version, which is the vector version of the equation, and this version, which is the symmetric, are all different ways to describe a line in 3 dimensions. Any questions about what we've just done? Now, if this is, and it is, the equation of a line, I should be able to take any one of the 3 versions and answer some pretty straightforward questions. So first one I'm going to do is imagine I've got the equation of a straight line, and it happens to be 2t plus 1, 5 minus 3t, and 4t take away 2. And I ask you a very simple question. Is the point 5, negative 1, 6 on this line? So the answer is going to be yes, it is, or no, it's not, right? So if you are the equation of a line, shouldn't you be able to answer that pretty straightforward question, right? Is this point on that line or not? Now, it's nothing like how you would deal with a similar question in 2D, right? It's different kettle of fish here. So what I'm going to do is I'm going to match the x coordinate of P, which is 5, with this equation. Then shouldn't that equal 5? Agree? The x should equal the x's. Now, the only way that's going to happen is that t equals 2. Now, if I find t equals 2, then I should be able to find what everybody is. 2 lots of t plus 1 is 5. 5 take away 3 lots of 2 is negative 1. And 4 lots of 2 is 8 take away 2 is 6. Is this guy him? And you see that they match. And so the answer is yes, this point is on that line. Do you like the logic of how I did that? I matched up the x's with 5, and I solved what value of t would you need for that one to match. And then didn't I just check that t worked for the second one? Did it give me this? And for the third one, did it give me this? And as you can see, it did. So the answer is yes. Suppose I had a guy, and it was 4t minus 1, 2t, and t plus 1. And it was the same question. Is P 7, negative 1, 0 on this line? Well, I would match the x's, and that would be that 4t take away 1, wrong direction, match the x's. So 4t minus 1 should be 7. That makes 4t should be 8, and that makes t equals 2 again. And then according to this formula then, R of 2 should be 4 lots of 2 take away 1, obviously 7. That guy's 4, and that guy's 3. Now, if you compare it against the point P, can you see that they don't match? So wouldn't the conclusion be here? No, that point is not on this line. So far, so good. For our last couple of questions for today, let's look at a question that would match what you would have done in the 2D world. Let's find the equation of a line joining the point 1, 0, -3 to the point Q, 2, 5, 1. So can you imagine that's P and this is Q, and what we want to know is the equation of the line passing through P and Q. Wouldn't that be very similar in, I don't know, Math 99? Find the equation of the line that passes through 2, 3 and 5, 7. Remember those kind of questions way back in the day? How do you find the equation of a line in 3D that passes through 2 points? Well, there are only two things I need to find the equation of every line. I need to know a point on the line. And the second thing is I need to get what's called the direction vector. B. If I know those two, can't I use the formula that we showed you at the beginning, right? Now, can you tell me the coordinate of any point on this line? It's not meant to be a trick question. Can you tell me the coordinates of any point on this line?
Yeah, you have the coordinates for P and Q.
Right. So I have a little decision to make here. Do I pick P? Do I pick Q? And I'm only going to pick P because I like P. But if I picked Q, it would also be the equation of a line, but it would be slightly different looking. So here's a weird thing. In the 3D world, the equation of a line is not unique. There can be many different versions that all end up being the same straight line. Now in 2D, isn't y equal 2x the line? There isn't another version that ends up being the same. I mean, you could play about with it, but essentially it's still y equals 2x when you rearrange it again. So equations of lines in 3D are not unique, which means if you're doing a homework question and it's like this one, isn't there possibly two correct answers? The one that you used with P and the other answer, the one that you used with Q. They'd be similar, but wouldn't one of them be using these three numbers and the other one would be using three different numbers? So you have to hope that WebAssign is clever enough to have more than one correct answer. So I've decided, for no other reason except I like P, to pick that one. How about the direction vector? Right, now direction vector is basically the direction that the line takes in 3D. That's a little bit less choice, isn't it?
Can you get the vector PQ?
That's the one you should use. Would you agree that one's a little bit more obvious? PEQ, right? What do you think would happen if I used QP? Do you think it'd be okay to use that as a direction for the line? Answer is yes. So doesn't that make it even more combinations around there? So pick the first letter for your point and pick PQ for your direction, just to keep WebAssign happy, right? So you're probably going to have the answer that WebAssign has. Well, let's see what PQ is. 2 take away 1, 5 take away 0, 1 take away -3, 1 add 3, you get 4. So I have my point, x naught, y naught, z naught, and my direction vector a, b, c. So the equation of this line could be that guy, 1t plus 1, 5t plus 0, 4t minus 3. And that is the equation of a line passing through 2 points. Now, suppose I decided to keep this direction vector, but I decided to use 2, 5, 1 as my point. The equation this time would end up being t plus 2, 5t plus 5, and what would the other one be? 4t plus 1. Do you see that it is a little bit different looking? I mean, there are a lot of similarities to it, but it's still a little bit different as well. Are we cool with that one? The equation of a,
I have no
yes.
idea where you get the t plus 1 and 5t or any of
Okay.
those numbers from.
Let me show you by writing the general formula down first. If you have a point x naught, y naught, z naught, and a direction vector v equal to a, b, c, the equation of the line will be at plus x naught, bt plus y naught, and ct plus z naught.
Oh,
So if you have P to be the point 1, 0, -3, that's what these guys are going to equal. And the direction vector happen to be 1, 5, and 4. That's what these guys are going to be. Then you put it together, you get one of these, 1t, plus, oh, plus 1. Then you're going to have bt, so that's 5t plus 0. And then ct, there's going to be 4t minus 3. So those three guys there, no, that's missing 0. They represent the coordinates of P. And the coefficients of T, which is these guys here, here, and here, they represent the direction vector. So 1, 5, and 4. That help?
yes, it did. Thank you.
So it's all a matter of just memorizing the general formula, which is this, and realizing that x naught, y naught, and z naught are the coordinates. And E, you know, the guy next to T, AT, BT, and CT, they come from here. That's A, that number will be B, and that number will be C. So for our last question for today, suppose I have found the equation of a line. And it's 2t minus 4, t plus 3, and -3t plus 1. And can you imagine this is the line they're talking about, right? It's going on forever. How do you find the coordinates of when a line cuts the, change that guy to 6 just to make my numbers easier, cuts the x, y line. So can you imagine that this here is the floor? Won't that line hit the floor sometime, right? If it travels far enough, won't it eventually reach the XY plane, right? That's the floor. And we would like to know the coordinates of that point. Now we've got the equation of the line written down in its space curve format. And we want to know when it hits the XY plane. So we have to figure out how we're going to tackle that problem. If you take any point that's on the floor, the XY plane, don't they all have the property that their Z coordinate is 0? Agreed? If you're on the XY plane, your Z coordinate will be 0, right? Your height is 0 if you're on the floor. Now I'm going to use that to find this coordinate. Won't this be equal to 0? So the Z coordinates have to equal 0 if it hits the XY plane. That makes negative 3t plus 6 have to equal 0. So negative 3t equals negative 6. So t equals 2. So if I know what t is, can't I then find the other two coordinates, the x and the y? So let's see what that would be. The space curve for this straight line is 2t take away 4. So 2 lots of 2 take away 4. T plus 3 is 2 plus 3. And we know what this one is 0, so I won't even bother calculating it. And I get the answer 0, 5, 0. We call that a position vector. So the coordinates are simply just 0, 5, 0. So if we call that guy Q, there's the coordinates of Q. Are we good? Suppose I wanted to find when the straight line met up with, say, one of the side walls, like the XZ plane. Okay, so imagine if this line traveled far enough, wouldn't it eventually hit one of the side planes? In this case, the XZ. What would I do to make that, solve that problem?
Set y equal to 0.
Which would make t, whoops, set y 0, wouldn't that make t equal negative 3, and then I could get the coordinates? Suppose I tried to solve that question, right? Is it possible for a space curve never to hit the XY plane? Could you imagine a line in 3D that never intersects with the floor?
A parabolic, maybe.
Oh, well, yeah, shapes could, but could a straight line? You're right, parabolic could miss the XY plane, right? Could just bend and not reach it. But what about a straight line? But here we go. This green pen, although you cannot see it because it's a 3D camera, is floating above the floor, and it's parallel to the floor. It's still floating above the floor, and it's parallel to the floor. Won't this pen never reach the floor? It's always 4 units above the floor for its life. So yeah, it's possible for straight lines never to reach any of the XY planes or YZ, whatever it might be. It's just kind of cool. So I think I should finish with a question. Can monsters count? Come on, Natalie, can monsters count?
Did you say monsters?
Yes.
I don't know.
Well,
Well,
in the cartoon, monster something, did they count?
oh, well, you might be close to it. They do count as long as you count Dracula. Oh, come on.
That was
Count
good.
Dracula. Come on.
Yeah, that's good.
Okay, your brain needs a bit of light humor because there's a lot in here. Right, I have already graded your test 1. I have sent out an email The email address that I used was the one that you used to sign into WebAssign. So have any of you noticed it should have arrived? Right. It's not that helpful yet. I mean, week one, so little has happened. You can't really say for sure how well you're doing. All it's got is 1 week's homework and one online test, which you may or may not have done well in. But as the weeks go by and more information is added, can you see it will then become a little bit more significant, right? You'll be able to tell how well you're doing. The midterm and the final are going to make a big difference. So you could have a really good grade, but do badly in those two, and that won't bode well for you. But of course, the other way could go as well. Could you do really good in those two tests, those two exams, and improve your grade a lot?